Chapter 8. Last week we talked about solids, liquids, and gases and got all the gas laws in our pockets. Now we're going to talk about solutions. We know what a solution is. That was introduced early on in the course. And we're going to introduce topics about solutions that are most important, actually. Solubility is one of them. And then we want to know how to express solution concentration so that we can use them in stoichiometric equations. And then we'll talk about colligative properties at the end. Let's see, no, that's not colligative property. Let's see, we got one, osmosis. Okay. Next week we're not going to be here. It'll be spring break. So that's why I went ahead and gave you molar mass by freezing point depression. Freezing point depression is one of those colligative properties that we'll talk about at the end of this chapter. And then after that, we do a lab on osmosis. And we're also going to talk about that today. All right. Remember, a solution is a homogeneous mixture. That is, it's a physical combination of two or more components. And these components retain their identity. That is, we can separate them by physical means. And they're homogeneous because no matter where you sample the solution, you get the same composition, the same percent composition for each one. Let's see, I think I have something. Hannah, right?
Yeah.
Okay.
So I was taking my baby into his mama's house. I grabbed my book bag and my diaper bag and took it both in and sat down. So I need some like scrap papers.
You could have the whole set if you want.
I didn't mean to set the book bag down.
Yeah, we got several copies. So that's that. Oh, here's the key for the work problems. And this, we're going to talk about this one today, solubility.
Okay.
You need the labs?
Yeah.
Yeah, you're going to need a lab today.
Yeah, I don't have my lab coat either. All that was in my book bag, so
Okay.
I need to buy.
We'll get you an apron. Take this one too. This one's for the week after we come back from spring break. Next week is spring break, so don't come in.
Thank you.
All right. Now these solutions can take several forms. In other words, you can combine two of the same phases and then get a solution, like alcoholic beverages, alcohol plus water plus a bunch of other stuff. You can dissolve the solutions that most people think of are a solid dissolved in a liquid or something dissolved in water, like sugar in water, salt in water. That's commonly what people think of. But solutions can also be a gas in a liquid, right? Every time you open a pop bottle, you hear some of that gas come out. You can dissolve gas in a liquid. We're breathing a homogeneous mixture, a solution right now, nitrogen and oxygen primarily. You can also have solid-solid solutions, alloys of metals, like brass is nickel and copper. You can't just slam two pieces of them together and get a solution. You have to melt them so they'll mix. And then when they solidify, you have a solid solution. We have definitions that we go by for solutions. And the first one is the solvent. You can only have one solvent. That is the major component in the mixture. But you can have many solutes. That's everything else. Now there are these rules generally hold true for all solutions, but there are some cases where you can start off with a major component of solvent and add a solute to it, and it goes into solution. You add some more, add some more, add some more. Eventually, you get to the point where you've got more solute in there than solvent. But we started off with the solvent as a major component, and we keep it there, like sugar water. You can make up a solution of sugar water that's got more sugar in it than it does water. And some solutions that have water as a component, we usually, not always, but usually assume that water is the solvent. Here we have some colored, I don't know what the crystals are, colored crystals dissolved in water. Right? The solute is the solid. So we have a solid and a liquid. Solid phase to start with. What do we have when we get finished? The solution is liquid. Right? Even though we started with a solid and a liquid, the solution is a liquid. All right. One thing about homogeneous mixtures, that solutions, is that they can have variable composition. Like I mentioned earlier, you can add a little bit of sugar or you can add a lot of sugar. And the percentage of the solute in relation to the solvent or in relation to the whole solution can change. And we still haven't changed the identity of the components. The solute and the solvent, they retain their chemical identity. But the solution as a whole, once you get those two together, the properties of the solution can change depending on how much of the solute you have dissolved in it. You can make, I can remember making a solution of water and hydroxymethyl cellulose, which is, I was using it as a thickening agent. It will dissolve in water, and the more you put in there, the thicker it gets. So we're changing the viscosity of the solution by changing the amount of the solute. I used to use it for, I was doing an experiment with protozoans. You know what a protozoan is? The different classes, we generally divide them into three. There's the amoebas. Paramecium is an example of another one, ciliated one. And then you have the flagellated ones like Euglena. Well, I was studying those for a high school project, and I wanted to take some pictures of them through the microscope. And they were moving too fast. They'd go across the scene, and I couldn't get a shot of them. So I thickened the solution with this hydroxymethyl cellulose, and they were struggling to move. Right, so I could get a good shot of them before they had a chance to leave the field of vision. So the properties of a solute and solvent together in a solution will change based on the composition, how much of the solute is dissolved in the solute, solute dissolved in the solvent. These solutes are in solution as discrete individual particles. They could be molecules, like you have a molecule of sucrose in your sugar solution, or if you dissolve table salt. When you dissolve table salt, or any ionic compound that goes into solution, that means aqueous. That is, this tells you what the solvent is. And what they do in solution, in aqueous solution, is they break up into ions. Right? But they're individual, they're discrete particles. Or if you dissolve You can dissolve elements, and some of them will go, let's see an example. You want an element that will go into solution but won't react with water. Otherwise, you don't have a homogeneous mixture anymore. You've created a chemical reaction. So I would think maybe the noble gases would be a good example. They would go into aqueous solution, but they would retain their identity as individual atoms. Another characteristic of solutions is they're homogeneous mixtures, but the solutes will not settle out. In other words, once they're in solution, they stay uniformly distributed in the solution forever until you do something to them. Change the conditions, and then maybe you can get some of them to drop out of solution. We'll talk about that in a minute. And I mentioned earlier that you can separate solutes and solvents by physical means, and there are a host of different ways to separate them. If we put sodium chloride in water, let's see, we did one of those already. Yeah. All you have to do is evaporate the water and you get your sodium chloride back. And there are other means. We use filtration, but that was a suspension. You had sand suspended in water. That's not a solution. But we did separate them by physical means. There are other possibilities. Chromatography is one. You know what chromatography is? No. We'll talk about it later. Okay, so in a homogeneous mixture containing 80 milliliters of water and 20 milliliters of alcohol, which is the solvent, which is the solute? The major component is water, right? So that's the solvent. And the minor component is alcohol. That is the solute. There we go. Now let's talk about solubility. This is a good example. We did, let's see, I want to be sure I'm signs of chemical change. No, we didn't do that one. Okay. Believe it or not, there is a point, a percentage amount of sodium chloride that you can put in water, and at a given temperature, that it will be a maximum. And any extra that you put in will not go into solution. Right? That's an expression of solubility. So many grams of salt, sodium chloride, will go into 100 milliliters of water. That's usually the way you find it in reference manuals. It'll be so many grams of this compound in 100 milliliters of water. That's an expression of solubility. Some compounds in aqueous solution are more soluble than others. Sucrose, for instance, right? Sugar, extremely soluble. You have to go very, very, very high in percent composition in order to reach saturation, where it won't anymore go in. Other compounds are less soluble, like silver chloride. If you have silver chloride in solution, just the tiniest amount will go into solution. And for all intents and purposes, we identify it as insoluble. Okay. Now the effect of temperature on solubility, most solids, when we put them in water, will become more soluble as the temperature is increased. You're increasing the kinetic energy of the molecules of water. You're increasing the kinetic energy of the ions or atoms of the solid. And that means that, well, they become more soluble. But there are exceptions. There are some compounds that are less soluble as we increase the temperature. And unfortunately, there's no theory that explains that yet. Maybe you can reason it out, but there's no solid chemical theory that will explain why that happens. So this is a practical matter. You just have to try it, see what happens. Or somebody else has already done it for you. And a reference manual should tell you whether a change in temperature will increase or decrease the solubility. Now this sodium chloride is a case where you increase the temperature, you get more salt in solution. In fact, that's the way I produce a solution that is saturated. I find out how much will go into solution at room temperature, say 25 degrees. I look it up, I weigh out that much and then get the right volume. And I add maybe 10% more in mass. And then I heat it up to where all of that goes into solution. And then I set the beaker on the bench top and let it cool down to room temperature. And one of two things will happen. Either it'll become super saturated, that is, all of it will stay in solution, but be very unstable. And if that's the case, then all I have to do is shake the beaker or scratch the inside with a spatula, and the extra will drop out of solution. And when it does that, let it settle, then the solution above that solid is saturated. I know it holds as much as it can at that temperature. Here are examples, right? Lead 2 bromide becomes a lot more soluble as the temperature increases. Cesium chloride is extremely soluble. I didn't realize that much. Grams per 100 grams of water. Let's see, do we have any? No, there's no examples here. There are no examples here of solubility decreasing with an increase in temperature. I think that's on the next slide. Or maybe we just tell it. Calcium acetate becomes less soluble as the temperature increases. No, I don't have that extra slide in this one. But that's just one example, and you have to determine it by experiment. Which ones will become less soluble as an increase in temperature? How about the effect of pressure? Well, if you're trying to put a solid into solution, pressure has no effect. If you're trying to put a liquid into solution, no effect. The only phase that is influenced by an increase in pressure and an influence on its solubility is a gas. As you increase the pressure of the gas over the liquid, more gas will go into solution. And that's uniform throughout. That always happens. There are no exceptions to that. So when we dissolve carbon dioxide in water and make pop, along with sugar and caramel coloring or whatever else they want to put in it, citric acid sometimes, phosphoric acid, yes. Anyway, when you want to put more carbon dioxide in solution, you do it under pressure. So when they inject carbon dioxide into the water and make soda water with sugar and so forth, then the bottles are capped immediately. Because if the temperature changes, if the temperature increases, then that gas is going to come out of solution. And you'll notice that if you go to a picnic and they've got 2-liter bottles of pop sitting out, and you crack a fresh one open, it'll go. You'll lose about half the carbon dioxide at that temperature because it's probably 80 degrees out. But if you stick that bottle of pop in the ice cooler or in the refrigerator for an hour, it'll cool down. And then when you crack the top, it'll go, you won't lose as much. Those are two effects. I'm describing two effects here. One is temperature and pressure. Once you've got the cap on it, then the pressure keeps that carbon dioxide in solution. When you release the pressure, then it comes out depending on what the temperature is. And for gases, that's probably on the next slide. For gases, increasing temperature decreases solubility. Well, I'll stick with pressure. Henry's law. Henry's law simply relates the concentration of the gas in solution in relation to its pressure. Concentration is directly proportional to pressure. And the proportionality constant is Henry's constant. Now, that constant, Henry's constant, is only constant for the particular gas, the solute and the solvent combination. Right, so it has to be experimentally determined. But for any given temperature and for a gas and a liquid combination, this will remain constant. And the more effective way to use this is the way we did with the other gas laws. Remember, if we had Henry's constant, now would be, let's see, C divided by P, right? So if this is the condition that at one stage or one concentration, one pressure, and this is for a different pressure, concentration will change, then these two are equal to each other, and C1 over P1 equals C2 over P2. That would be a more useful equation, just like our gas laws when we had before and after situations. We did talk about that, didn't we? Let me see. Let me be sure. Because when I discuss gas laws, I always talk about those. Yes, we did. Okay. Well, I guess we're going to hold that thought on temperature and gas solubility. Saturated solutions, I mentioned earlier. Once we reach saturation, then there's no more apparent dissolution of the solid. In other words, you will have a certain amount of solid maybe on the bottom of your beaker, and apparently it looks the same size from then on. But what's happening at the molecular level is that you're getting, so here's your solution, and here's your solid. And in the beginning, you'll get solid molecules or ions moving into solution. But eventually you get enough up here that now they go both directions, right? And at the microscopic level, this activity is furious, right? It's happening at, my dad used to say, lickety split. But what we observe is that the amount of solid now is not changing. That solution is saturated. And that's what we're trying to illustrate here. That situation where I mentioned creating a saturated solution, only when I heat it up and then let it cool down, everything stays in solution. Now, it doesn't always happen, but it can happen. And in that case, you're producing a supersaturated solution. One thing about a supersaturated solution is it's very unstable. In other words, if you look at it cross-eyed, the extra solid will drop out of solution. Or if you shake it or you scratch the inside with a spatula and you create little imperfections in the glass, then you provide for the solid nucleation sites where the solid can cling, and the extra solid drops out. The other possibility is to just take a crystal of the solid and drop it in there. And that'll give the solid something to nucleate on, to be attracted to. And that will cause it to not be supersaturated. It was the amount of solid in solution will decrease to the point where it's now only saturated. Anything less than saturation is known as unsaturated. In other words, you can put more solute in that solution. And these are qualitative terms. Some more qualitative terms. If we have a solution that's close to its saturation point for a particular solute, we say it's concentrated. If we have one that's very far from the saturation point, just very little solute in it, we call it dilute. And there's a continuum in between them. We can do that with acids. Right? We have bottles of concentrated sulfuric acid in the storeroom that's 98% by mass sulfuric acid. We have concentrated hydrochloric acid, and it's usually about 35 or 37%. We have nitric acid that's concentrated, and it can be higher than this, but we usually buy 70%. And so those are concentrated solutions of those acids. Actually, we've got a bottle of 100% acetic acid, the stuff you make vinegar out of. It's called glacial acetic acid. In that case, it's not a solution because it's 100%. Okay. What we've got here is a comparison of a dilute and a concentrated solution using the same solute that gives it that blue color. And you'll notice that as both beakers have the same amount of that blue substance, but they have a different amount of the solvent. So if you decrease the amount of solvent, you concentrate the blue solute, and the color becomes deeper and deeper blue as you concentrate it. Actually, you can readily see through the one on the right because it's more dilute, but the one on the left is more opaque. You can't see through that. We use that difference in devices we call spectrophotometers, right? We've got two of them sitting over there. The ones with those dials on them, you see with the black knobs on the front, those are spectrophotometers. And we can, if they're calibrated properly and we use the right wavelength, we can actually measure the concentration of one of these solutions because of what we call the optical density. In other words, we've got more of that blue substance in there, and we can measure it optically. All right. We can have, if we have aqueous solutions, we'll designate those with whatever here, followed by aqueous means that the solvent is aqueous. But we can have non-aqueous solutions also. And we mentioned a few of them in the beginning. You can have different phases combined, which means you can also have different solvents. Organic chemists conduct a lot of their reactions in non-aqueous solutions for the simple reason that water, the types of reactions they use to synthesize organic compounds, in those reactions, water becomes a reactant. And they don't want it because that'll produce the wrong reaction. So they make solutions with some other type of solvent like toluene, an organic solvent. I used to use benzene a lot, but that's frowned upon now because benzene is carcinogenic. Anyway, they don't have to be aqueous. We're going to concentrate on aqueous solutions. It's just simpler that way. Okay. Increased temperature decreases gas solubility. That's true. Think about it this way. If you have an aqueous solution of gas, think of it as these little circles are the gas molecules. Right? And they're in solution. And if at a given temperature, you can have so many of them in there. If you heat it up, what are you doing? You're increasing the kinetic energy of not only the solvent, but the solute. And kinetic energy means that at the surface, both the solute and the solvent have enough energy to escape into the gas phase. Okay, so if you increase the temperature, you're actually driving those dissolved gas molecules out of solution based upon their kinetic energy. So when you put water on the stove to boil, what's the first thing you see once it gets hot? You see little bubbles form, right? Okay. That's not water vapor. That's dissolved gas coming out of solution first. And then after that's all gone, then the temperature rises high enough to so that the vapor pressure above the surface of the water is equal to the atmospheric pressure. And at that temperature, the water will boil. Okay. Now here's a theory about how solutions form. If you have a solute here, solvent here, and you want to make a solution of those two, think of it in terms of the particles in each one, the molecules or the atoms or the ions in each one. In order to get them to become miscible with one another, we have to do three things. Well, first you have to do two things. First, you got to break the bonds that are holding the solute together, right? So you have to add energy. So you input energy, which is an endothermic process. You got to break those apart into particles. So that costs you energy. You got to put energy in. Same thing for the solvent. The solvent's molecules have some attraction for one another, some more than others. Water is a lot of attraction. So you got to put a lot of energy into it. And this is also an endothermic process. Let's see. We've got them numbered here, don't we? Solute is 1 on that slide. This one is 2. You're breaking the bonds of the solvent and the solvent, the solute and the solvent. And then when they come together, they're farther apart. And when they come together, they obtain a lower energy state. Right? And remember, energy is conserved. So if they have high energy apart, they come together at a lower energy state, we have to give up that energy. And that's an exothermic process. That's the third step. Now, if you form a solution with a solvent and the solution gets hot, that means it's giving off energy, and it's a balance among these three conditions. That means that you got a whole lot more energy back than you put in. That makes it hot. If you go to a hospital and they grab one of those bags and break a capsule and mix it up and it gets cold, that means you have to put a whole lot of energy in and you get very little of it back. So it sucks up a lot of energy without much return. Okay, that explains the difference in hospitals between cold packs and hot packs. It's a different chemical inside the capsule when they break it in that water bag and mix it together. Now, this is what we call a thermodynamic process. It's an equilibrium. It doesn't care about what happens in between. You do this, you do that, you get this, and how fast it happens is another issue. It can happen really fast. It can happen really slow. But if we want to affect the rate, we can do some things that will change the rate of solution formation. since, and I think this first one, we're using an illustration of a solid in a liquid or a solid in water. If that's the case, then the dissolution process, let's take sodium chloride, right? It's going to be a cube. This is sodium chloride. How does it go into solution, right? How does it get dissolved in water? Well, the water has to go to the surface of the cube and pull off an ion. It has to hydrate the ion. Sodium ion, chloride ion, sodium ion, chloride ion. Everything happens at the surface. So if you increase the surface area for a given mass, that means particle size. You break this thing up into smaller particles, that makes more surface for that mass. And that will speed up the process because now water has access to more surface area. That will increase the rate of dissolution based on particle size. You can also agitate. Right? So if this crystal is sitting right here in water and we're pulling off sodium ions and chloride ions, what happens is they're hydrated close to the surface. We form a layer of hydrated ions close to the surface of the crystal. And that means fresh water molecules can't approach and remove more ions. It's more difficult. They have to work through a concentration gradient. But if we agitate it, that moves these away and introduces unassociated water molecules close to the crystal. That also increases the rate of dissolution. In some cases, it just says temperature. So for most solids, you can increase their solubility by increasing the temperature. For some solids, decreasing the temperature will increase their solubility. For gases, all gases, if you decrease the temperature, you increase the solubility. So temperature has an effect also on the rate. And then the last one is the common ion effect. So we have to be talking about ionic solids dissolving in a liquid. And so if you have an ionic solid here, right, with a cation and an anion, and you want to put it in solution as this, and let's put it in water, makes it easier. Right? You want to put those in solution if you already have ions like this in the solution, then they will decrease the speed or the rate of dissolution of any more solid that you put in. There's competition for space in the solution. So what you should see actually over time, as you increase the concentration of the concentration of your ions in solution, you should see over time the concentration. Well, that's not a good example. I need rate. How fast is it going? All right, so let's say velocity. So let's say grams per second going into solution. You should see in the very beginning, when you've got pure solvent, the rate is going to be high. You're taking it into solution because there's no competition from dissolved ions. But as you start to increase the amount of ions in there, the rate of dissolution will go drop down until you reach saturation, and then it'll stop. So that common ion effect, if you already have those ions in solution, will decrease the rate of solubility or rate of dissolution. All right. So can we determine what is soluble and what is not soluble in water? And the short answer is yes, we can. There is the overriding concept is polarity. Right? Have we talked about polarity yet? Let's see. When we talked about bonds, didn't we talk about polarity? Polar bonds? I'll refresh your memory. Okay. Let's take water as an example. If we have H2O and the structure of water is like this, it's a bent molecule. Okay. There's a term we use called electronegativity. And that simply means that in a covalent bond, elements have different strengths of attraction for electrons. So this is a shared bond, 2 electrons each, right? But oxygen has a stronger pull on the electrons in that bond than hydrogen does. So the electrons tend to spend more of their time around oxygen than they do close to hydrogen, even though they're shared. So we say that oxygen is more electronegative than hydrogen, and the bond between the two is polar. And we use an arrow with a plus sign on one end. This shows you the slight positive side of the bond, and this shows you the direction of electron movement. So that means this would be slightly positive, and this would be slightly negative. Okay? That's what this is, a Greek letter delta. And it just means slight. It's not a full charge. If it was a full charge, we would no longer have a covalent bond. So what that does is these bonds now are polar. But how about the whole molecule? Well, since the electron pull is going both this direction, we have an overall polarity of that direction. Okay, so one side of the molecule is slightly negative and the other side is slightly positive. That has an effect on solubility. If your solvent is water and your solute is a soluble salt or another polar compound like ethanol, right, alcohol, then they will each go into solution more readily. If, on the other hand, your solvent is nonpolar, say your solvent is benzene, which is a ring compound like this, with these, everywhere you see these lines meet is a carbon. And then you have one hydrogen out of each one. That's a nonpolar molecule. If you try to dissolve sodium chloride in that, or you try to dissolve alcohol in it, it won't go. What we're getting at is this, in green, is like dissolves like, and we mean polarity. Like polar solvents dissolve like polar solutes, and nonpolars dissolve nonpolars. There are exceptions, but that rule holds for most things. All right. However, we've learned that at least for aqueous solutions, there are some salts, right? There's some combinations of cations and anions that do not significantly dissolve in water. We call them insoluble. And that's where we can use the rules, right? If this were a class where you're going to major in chemistry, you'd learn the rules. But since this is not, it's like it's an introductory course to set you in some other direction. That's why I created that. Well, I didn't create it. I give you copies of that chart with the grayed out squares and the clear squares. But it's based upon these rules, right? And we're not going to go over the rules because you don't need to know them. So there's your chart. And you'll notice that the way it's set up is the cations are across the top and the anions are down the left-hand side. So if you want to find out if a salt of a cation and an anion, a combination like that, is soluble in water, you find your cation and you find your anion and you follow them down to where they meet. And if it's grayed out, we consider them insoluble in water. And if it's clear, they're soluble. So for example, if we go over here to, I mentioned silver chloride before. There's silver right there at the top, right there. And if we go down to where it meets chloride, right here, right, there's chloride over there. Silver chloride is insoluble. So use the chart. And before I misspeak, let me look at the exam and be sure that chart is in the exam. Well, not in this copy. Right, so, of course, if you're taking the exam in person, then I'll hand you a copy of this. If you're taking it on, if you have to take it on Brightspace, right, you can't come in that day, then it's okay to keep that with you while you're taking the test. All right. If there are very large differences in polarity between the solute and the solvent, then you should expect them to be less soluble. Okay. The difference, right? Polarity is expressed on a continuum. In other words, you can have extremely polar molecules and extremely nonpolar molecules, and then there's all this space in between. The closer the solvent and the solute are to one another in polarity, the more soluble they will be. So, which of the following ions in this group form generally soluble compounds with lead 2+? So there's our cation. And we want to associate anions with it. Right? Sulfur, chloride, nitrate, and sulfate. And put another cation down there. That's a gotcha. You don't form salts with a cation and a cation. Right? So we can throw that one out. Okay, so we take the others and we look at the chart. Let's go back. Since I got them on the board now, we can back up. There we go. Look at the chart and find lead 2+. Right? It's way over here on the right-hand side. Come on. Where's my arrow? Oh. Let's see. There we go. So there's your lead 2+. So we follow it down, find sulfide. Lead 2+, lead 2 sulfide is right here. It's insoluble. So when you put these two together, you get a solid. How about lead 2+ and chloride? Well, let's see. Let's find chloride. Chloride and lead 2+ are, I can't get it to work now. There it goes. Chloride, that's insoluble also. How about nitrate? All right, lead 2+ and nitrate is right here. It's soluble. So we give that aqueous. It goes into solution. How about lead 2+ and sulfate? Now, let's see, sulfate is way down here. It's insoluble. So the only one that's soluble is the nitrate. And if you learn the rules, you'd know that all nitrates are soluble. Every one of them, no exceptions. All right. There's your answer. All right, now we need a way to express concentrations. Remember we introduced the topic of variable composition. Mixtures can have variable composition. We need to express that composition in some form that is useful. And it depends on the application as to which one we use. We want to express it some way so that we have an amount of solute per amount of solvent, or sometimes we include the amount of solute in there. So this would be relating the amount of solute to the amount of solvent in one type of expression, or the amount of solute to the amount of solution in the other possibility. Percent concentration. Let's see, I think we have. We're going to follow that with a slide that talks about it. Yes, okay. These are possibilities. Percent concentration and molarity are the two most common. Percent concentration, we have to be careful with percent. You know, I've mentioned that before. When you say percent, what does that mean? If all you see is percent, it just means parts of solute per 100 parts of something else. It's not specific, it's dimensionless. So what we need is to specify what we mean by that. Right? And if we're talking about a percent concentration, we want to say what grams of solute per 100 grams of solution. That's the most common percent expression for percent. I'll talk about molarity in a minute. Let's see, so that's percent composition. Then we have molarity. And then a third one is molality. When we do that lab, when we come back from spring break, we're going to determine the molar mass of a compound based upon its freezing point depression. And in that one, we have to use molality rather than either one of these. All right, so let's get to the definitions. Well, just to expand on this one, percent is mass, grams of solute per 100 grams. This would be mass percent. We would usually say mass, like that. Percent by volume would be percent volume. So that would be so many milliliters of solute per 100 milliliters of solution. Okay. Or you can combine them. You can say percent mass volume, and that would be grams of solute per 100 milliliters of solution. Okay, percent by mass is really easy to calculate, and it's independent of temperature, right? If you change the temperature, mass is not going to change, right? Mass is a measure of amount, no matter what the temperature is. So that's one of the advantages of using this type of expression, because it's independent of temperature, has no effect. So we just have mass of solute and a mass of solution times 100. And always remember that the mass of the solution is the mass of the solute plus the mass of the solvent. Now, if you have more than one solute in there, you got to add them all up. Add the mass of the solvent plus the mass of all the solutes is the mass of the solution. And then you just put in the numerator the mass of the solute you're interested in. So let's see. Percent by mass concentration of glucose in a solution, dissolve 5.5 grams of glucose in 78.2 grams of water. So this mass percent of glucose would be 5.8 grams of the, 5.5. 5.5 grams of sucrose, and then the mass of the solution also has the sucrose in it, plus the water, times 100. And that would be the mass percent, 6.6%. Now, we probably should have put in parentheses M divided by M, just to be kosher. Volume percent. Where do we commonly see volume percent? Alcoholic beverages, beers, wines, booze. Except for distilled liquors are sometimes quoted as proof. I'll get to that in a second. But the volume of the solute divided by the volume of the, that's an error. It needs to be the volume of the solution. So if we have 30 milliliters of methyl alcohol and 435 milliliters of solution, let's see if that comes out to 30 milliliters divided by 30. Well, you know what? It gives us the volume of the solution. And if you're interested, when you combine two volumes, the volume of the solute and the volume of the solvent, if you know the volume of each, the volume of the solution may not be the volume of the addition of the two. Because once they mix together, some of the volume of the solute may go into that empty space that's taking up in the volume of the solvent. All right, so the total volume may go down. Or if they repel one another slightly, the volume may go up. All right, so you need to know the final volume by measurement. So that's 30 divided by 435, right, times 100. And that's 6.6%. All right, so that previous slide has an error in it. Right? Oh, excuse me, 6.9%. Percent, volume, or you'll see it on the bottle, a bottle of wine, you'll see it A, B, B, alcohol by volume. Now, if you've got, if it's expressed in proof, you just multiply this value times 2, right? Because 200 proof is 100%. So 2 times that would be what? 13.8 proof. That really doesn't have much meaning because proof is used for distilled liquors. All right, mass volume. In this case, you need to know the volume again of the solution because when you put the solid or the mass of anything into the solvent, the volume may change. So you have to measure the final volume. All right. Those are examples. And once you have that percent, remember, anytime you have a ratio like this, let's see, let's do this. Once you have 6.90 milliliters, I think they were using methanol per 100 milliliters of solution. Once you have that ratio, you can use that as a conversion factor. All right? Let's make some room here. So let's say you have 300 milliliters of solution. Then you have 300 milliliters of solution that's 6.9% volume or alcohol by volume. Then we can use the conversion factor. This is milliliters of solution. So we need milliliters of solution in the denominator to cancel these two, right? So there we have 100. And on top we have 6.90 milliliters of methanol. You don't want to drink that one. That's wood alcohol. That's the one that makes you go blind. So we would cancel these two here that make 3. 3 times 9 is 0, 7, and let's see, 2 plus 18 is 20. That means we're talking about 20 milliliters of methanol in that volume. So you can use these as conversion factors. If a solution has 10% by mass, that means it has 10 grams of solute in 100 grams of solution. So if 10% or 10 grams of that 100 grams is solute, then the other 90 grams is the solvent. Right, so that one, it correctly answers that question. All right, this is one. Trying to think if we haven't already done this one. Or we may not do it in this course. That's the problem in my mind. No, we are going to do this. When we get to osmosis, we're going to do this type of calculation. The osmosis lab will do this calculation. How many grams of sodium chloride are needed to prepare 150 milliliters of 0.9% mass volume? Okay, so we have 150 milliliters of solution, and we need to know how many grams of sodium chloride to give us 0.9%, 0.9%, which is 0.9 grams of sodium chloride per 100 grams of solution. Right. So actually what we have here is a ratio, correct? So all we need is 150 times 0.9 divided by 100. And that should be 1.35 grams. The other way you can do it is say if you have 150 milliliters of solution, then use the 0.9% as a conversion factor. And you have 0.9 grams divided by 100 grams of solution. And that gives you the same answer. So you can treat it as a ratio or treat it as a conversion factor. Comes out the same way. Okay, now let's talk about molarity. Molarity is probably the most used expression of concentration in chemistry. And we give it this capital M. So if we put a number in front of it, that means something molar. And the calculation is simply the moles of the solute. Right? That's what my N means. N means moles per volume in liters of solution. Okay? So moles divided by liters is molarity. And when you do this calculation, just like this, that has to be moles and that has to be liters, without exception. So if we were to express 1 mole of sugar, I assume that's sucrose, in 125 milliliters of solution, what's its concentration in molarity? So molarity is going to be 1 mole of sucrose in how many liters is 125 milliliters? Remember, if the unit gets bigger, then the number gets smaller. All right, so there are 1,000 milliliters in a liter. That means we need to move 1, 2, 3 places over, 0.125 liters. Divide that into 1, and that'll give you 8 molar. Eight molar in sucrose. The nice thing about molarity, well, there's several things actually. But one of the nice things is once you've expressed this concentration, once you've got so many moles of the solute, then the concentration is independent of what produced the moles in the first place. Right? It could be moles of anything. And it's a more efficient way to compare amounts of different compounds, especially when we're talking about chemical reactions. Because remember, chemical reactions occur by numbers of things, not by mass. So if we have solutions that we put together for a chemical reaction, then if we have molar concentrations of each one, then we need the balanced equation, of course, but we can calculate the number of moles before we move to any other part of the equation. Remember, you can't move anywhere in equation for stoichiometric purposes unless you have moles. So here we go in the other direction. Then we have a solution that's 10 molar in sucrose. We want to know what volume do you need to have 2 moles of sugar. So we have 2 moles of sugar, but we want to know what volume. So this is like any math equation. If you've got one unknown, you can solve it. So if we put the volume over here and the molarity over here, remember molarity is moles per liter, and the moles cancel, and liters is in the denominator of the denominator, which is the numerator. Right? Then we have, let's see, that's 1/5 or 0.2. 0.2 liters. That's the volume we need of that solution to guarantee that we possess now 2 moles of sugar. Okay. Now, if we have 0.2 liters, how many milliliters do we have? Because most glassware is not calibrated in liters. Yes. 3 places to the right, 200 milliliters. Yep, exactly right. So let's consider the point of this slide. Let's see how we did 10. Okay. The point of this slide is to show you that equal masses of different compounds in the same volume will not produce the same molar concentration. All right, so if we have 100 grams of sodium hydroxide, I think that's right, yeah, and 100 grams of potassium chloride, oops, in what volume? 250 milliliters. Right? So each one is going to be a separate solution of a final volume of 250 milliliters. So what we have to do is convert to moles first. Right? How do we do that? Right? Cancel the grams, leaves us with moles. Anytime you have a quotient with grams and moles, you're talking about molar mass. So what's the molar mass of sodium hydroxide? Well, let's see that we have to add it up. I can't see that far. I need a periodic table. Okay. Here we go. Sodium, 23. All right, so we have 23 for sodium, oxygen is 16, and hydrogen is 1.01. 1, 0, let's see, 9, 10, 4. Grams per mole, 40.01 grams per mole. How about potassium chloride? Potassium is 39.10. And chloride is 35.45. So that's 5, 5, 14, 74.55. $74.55. There we go. So we find out how many moles. Oops, I need my calculator. Find out how many moles of each that we're going to put in 250 milliliters, separate solutions. Let's see, 100, 40.01, that's 2.499 moles. So the molarity of this solution is equal to 2.499 moles divided by 0.250. Let's see. Liters. And that's, well, rounded off, it's 10.0 molar. How about this one? Let's see. 100 divided by 74.55 is 1.341. 1.341 moles. So molarity is equal to 1.341 moles divided by 0.250 liters, which is 3 significant figures. 5.37 moles. So with the same masses of two different compounds, we get two different molarities. Okay. All right. Now let's talk about dilutions. This is something I used to do on a regular basis in the laboratory. The reason we're talking about preparing a stock solution, a more concentrated solution of a mixture of different solutes that I want to use to, say, extract a soil. But the solutes go into solution kind of slow. All right, so you don't want to have to make that up every day because I got to do 200 or 300 samples a day. So you make up a more concentrated solution, and we used to keep them in big carboys like this, lots of them. And then we would take a certain amount of that and dilute it with extra solvent to the right concentration of each one. They're already at the right ratio. Right? We don't change the ratio by adding more volume. We change the total concentration of each. So how do we do that? Well, let's say you have your stock concentrated solution over here with a molar concentrated molarity there. Okay? And you want to dilute it to a known volume in a volumetric flask. Okay? These flasks are extremely accurate. Right? They're like, I don't know, like 5/100ths of a milliliter in a liter error. They're very accurate. So let's say this one is at that mark, we would have 1 liter of solution in that container. Okay, this is going to be at a different concentration, the diluted concentration, because we're going to take some of this one out, put it in there, and then add more solvent. So we're diluting it by adding more solvent. So we take out a certain volume here. This is volume of the concentrated amount. And we deliver that volume in here. Okay. So in this case, that's the volume that comes out of here. The volume over here is the total volume of this container. All right. Now, what's the same in both of these situations? The same is the number of moles. The moles from the concentrated goes in here, moles of the dilute, they're exactly the same. Both of them. Okay. So how many moles did we pull out of here? Well, if we consider the expression molarity equals moles divided by volume, then moles equals molarity times volume. So this concentrated one is the concentrated molarity times the concentrated volume. Okay? And over here, we put in a certain number of moles, and that's equal to the molarity of the dilute times the volume of the dilute. Okay? So we've got these two expressions. This is a different concentration and a different volume, but it gives us the same number of moles as this one. So remember, if A equals B and B equals C, then A equals C. Right? If these two are equal to that, and this is equal to that one, then these two are equal. Right? Mathematically speaking, they're exactly the same. So now you have an equation. All you have to do is be sure that you put the numbers in the right place. Okay? So that's why when I read a problem, and sometimes it's given M1 V1 equals M2 V2. Either way works. But when you read a problem, you ought to set up a table. If it's a dilution problem, put your values in and find out which one's missing. Let's say this is missing. You want to know what volume you need to pull out of this one at that concentration to give you this concentration with this dilution volume. Okay, So you just need one of them that's unknown. So you look at the problem and say, all right, put them in the right place. And of course, the question is going to tell you which one is unknown. All right, so let's take an example. These here, those there, and we'll leave those there so we can put that information up there. How would you prepare 100 milliliters of 0.9% saline solution? So what's 100 milliliters? Is that this volume or that volume? It's the diluted volume, right? So you want 100 milliliters. At what concentration? 0.9%. Okay. And your stock solution, your concentrated solution is 10%. And that's your unknown. So if we solve for this one, now we can plug in the values in their proper place. And notice, these are all ratioed. So if we use the same units of concentration here, and this is, I see why they use C for concentration, because we're using molarity, but it works for concentration also. If we could do this, we could do that. So in this place, we've got 0.9%. And in this place, we've got 100 milliliters. And in this place, we have 10%. So 0.9 divided by 10, let's see, 0.9 times 100 divided by 10 would give you what? Well, I'm sorry. Yeah, 9 milliliters of stock. So this would be 9 diluted to 100 milliliters. Now, if we assume that the volumes are additive, then you can say 9 milliliters plus 91. But I hesitate to do that. If I want to be accurate, I have a 100 milliliter container that's accurately calibrated. And then I would put the 9 milliliters in that one if this were 100 milliliters now. Put the 9 milliliters in there and then fill it up to about here, mix it really good, and then finish up to the mark.
Dr. Bob,
Yes.
I have to step out a second to use my phone to call my social media tuition.
Okay, no, that's fine. Okay. Let's see. Here, okay, here we are. We're doing on time. I think we can get it finished. Okay, that's dilution. All right, let's see. A 0.5 molar solution of sodium chloride sits on a lab bench. Which of the following would decrease the concentration of the salt solution? Adding water to it? Oh, yeah, water's the solvent. If you add a solvent to it, then you add more in the denominator. Right? Let's see. But if we're using molarity, right? You add more of this, increase the denominator, and this will get smaller. So A would work, yeah. Pour some of the solution down the sink. No, because it's a solution, so you're pouring the same ratio goes down the sink as that stays in your container. All right, so B wouldn't work. Add more sodium chloride? No, that's the solute. You increase the concentration. We don't want that. Let the solution sit out in the open air. Sodium chloride is not volatile, so the only thing that's going to evaporate is the solvent, and that will increase its concentration. So D won't work either. At least two of the above would decrease? No, it's just the one. Just add water to your solution and you'll dilute it. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar? All right. So if we go back to our equation, let's see, let's do concentrated. Concentrated times volume concentrated equals molar dilute on dilute. Okay. Let's see. What's the concentrated molarity? 2 molar, right? The question is, how much of that do you want to bring out? And your target is 0.8 molar in a final volume of 150 milliliters. Okay, so now we can plug in our values or solve for the unknown. We'll do that. Okay, so now we can put in 0.800 molar and volume is 150 milliliters and molarity of the concentrated is 2. Notice I don't have to change the milliliters because we're in a ratio situation. If I leave this milliliters, then this answer is going to be in milliliters. All right. All right, if we do calculations correctly, this volume is 60.0 milliliters. Now, if you calculate the molarity as an independent calculation, by its definition, moles per liter for volume, the volume must be in liters. But if you're in a situation like this, where you have ratios, then you don't have to change the units of volume. All right. Now, up to this point, we've been talking about solutions as homogeneous mixtures. There's another type of homogeneous mixture that is not a solution. It's called a colloid or colloidal dispersion. It's still a homogeneous mixture, and the particles that we would normally identify as solute are dispersed uniformly throughout the dispersing medium. So our solute now becomes a dispersed phase. And our solvent, now we identify as a dispersing medium. The formation of a colloidal dispersion is based upon particle size. The particle size of the dispersed phase is small enough so that the kinetic energy of this dispersing medium particles is sufficient to keep the dispersed phase suspended. This is a suspension. Now we worked with a suspension before, right? Sand in water. Right? Those particle sizes were just way too big, right? Within a second, they started dropping out. But if you make the size of the particles very, very, very small on the same order, similar order to the size of the dispersing medium, then the kinetic energy of these dispersing medium particles, when they bang into the dispersed phase, they can keep them suspended. Now, the way we tell them apart, the difference between a solution and a colloid is we use what's called the Tyndall effect. Okay? So if we have a light shining from the side, produces a beam, and we position our eyeball on the other side, then we can see that light coming through the solution. And if we're on the other side, or your eyeball's out here, I have to put it down here because this is only 2 dimensions. You see nothing. That is a solution. However, if you do see some dispersion of the light beam in that mixture, right? So you can see that light beam. This is a colloid. Okay, that's the Tyndall effect. Let's see if I've got a slide for it. Yeah, there we go. So here we have a solution is on the left, the kind of the orange one, yellow-orange, and the reddish one on the right is a colloid. And you see on the left, you can't see the light beam in there because the particles are not just suspended. Those molecules are intimately in the mixture. It's based upon particle size. The particles are only suspended in the colloid. That means they are able to disperse light beam. So the Tyndall effect tells me the one on the right is a colloid and the one on the left is a solution. Now, we're not going to use that effect in the lab, but my general chemistry class does use that in the lab. One of the types of titrations they use, it's very difficult to see the endpoint because the endpoint is formed by a precipitate. And the precipitate, you detect the precipitate with the Tyndall effect. And you can get very, very close to the endpoint there. But that's how you tell the difference. Now, I said this is a suspension. It's a type of suspension. The authors of your text say that suspension has to be heterogeneous. So this is kind of in between, right? This is a colloid is in between a homogeneous mixture and a heterogeneous suspension. They have to be heavy enough to settle out. It may take them a long time, but if it does take a long time to settle out a suspension, there's something you can do about that. And it's called a centrifuge. Now, a centrifuge, let's see, we've got a couple of them, those round things sitting over there. If you put your suspension in tubes, balance them correctly, and then spin them up very fast, you're simulating a gravitational field, right? A centrifugal force. And that accelerates the separation of the suspended particles from the suspension medium. Okay, and you can get these things going thousands of RPMs. Right, we used to have one in a research lab in the USDA that would spin up to 150,000 RPM. I think it's really high. it spun so fast, it had to be refrigerated because it generated a lot of heat. And put the centrifuge head into the machine and then close the door and evacuate it. So you wouldn't have any friction with air, right? It moved that fast. But you're simulating gravity is what you're doing. Right? Have you ever been to the fair where they have that thing that spins around with carpet on the walls? Everybody stands there, and once they get it going fast enough, the floor drops out. Right? You're experiencing artificial gravity, right, against the walls because you're spinning. And that's what the centrifuge does. And it can separate the suspended particles much faster that way. Okay. Let's see. That's straight out of your book. I'm going to let you look at that at your leisure. A colloidal dispersion is a mixture that contains small particles not visible to the naked eye. Yes, that's true. They're microscopic. It's a mixture that contains particles that do not settle out under the influence of gravity. True. You can even put them in a centrifuge and they won't settle. A mixture that contains particles that cannot be filtered out through large pore filter paper. So they had to say large pore because you can, if you make the pore small enough, you can filter a colloid. Now, what are some practical colloids? You like Jell-O? Jell-O is a colloid. And it's water and gelatin and color and flavoring. But that colloid, the suspended medium, is a protein that's derived from animal hooves and bones. All right, so they don't let the carcass go to waste. They extract the gelatin protein from the bones and the hooves and make Jell-O out of it. All right, so now you're not going to eat Jell-O anymore, are you? Okay, let's talk about colligative properties. All right, colligative properties. And these are properties of solutions. What we mean by colligative property is, first and foremost, it's a physical property. In other words, it says nothing about the chemistry of the mixture. And it depends only upon the number of solute particles. In other words, the concentration of the solute particles in the solution is the only thing that causes variation in the property. Right? And we're going to look at 4 of them. The vapor pressure depends upon the number of solute molecules in the solution. The boiling point elevation, so we got a temperature change of the boiling point. The boiling point will elevate as you add more solute. You will increase the boiling point of that mixture. And freezing point depression is the one we're going to use when we come back from break. And the last one is osmotic pressure. And we use the capital pi for that one, like pi r squared. No, pi r not squared, pi r round. Those are colligative properties. Now let's look at each one. The vapor pressure will change for a solution depending on how much or what, how much of a solute is dissolved in the solvent, right? And the controlling law, the law is written as Rayo's law. What it says is that the pressure, the vapor pressure of the solution, right, solution, is equal to some factor times the vapor pressure of the solvent. So what is that proportionality factor? It's called the solvent. This is the mole fraction. Mole fraction of the solvent multiplied by the 100% vapor pressure. I've described vapor pressure to you before, haven't I? Let me do a quick reminder. Let's say you have an Erlenmeyer flask. And in the bottom of it, you have some liquid. All right, so at a given temperature, the liquid is going to form vapor from the liquid. Liquid's going into the gas phase, right? If it stays open, it just keeps going until it's all gone. But if we cork it, seal it off, then you eventually get enough vapor molecules up here that they start returning. Right? Gas goes back to liquid, and we get a balance. Eventually, you get a balance between vaporization and condensation. All right? At a given temperature. And the depending on the nature of the liquid, you get a certain vapor pressure built up in this space. That would be the pure vapor pressure here. Okay? Now, if we change the concentration of the pure solvent by adding some non-volatile solute, right? Like we put maybe sodium chloride in here. And what that does is by two processes, it restricts the vaporization of the solvent. One is these sodium and chloride ions attract the solvent and prevent it from leaving the surface. And the other is they just get in the way, right? Right at the surface, you've got sodium chloride ions at the surface, and that means there are fewer of the solvents molecules at the surface to escape. So we reduce the vapor pressure. What we need to know is what is the concentration of the pure solvent in that mixture. And that's where the mole fraction comes in. And the mole fraction is simply the mole fraction of the solvent is simply the number of moles of solvent per total moles. Right? Combination of the solvent and the solute. Okay? Once you know that, then you plug that in here, and this is given for a particular temperature, then you can calculate the new vapor pressure. All right? Now, usually, we're given so much of the solute dissolved in the solvent. And we would calculate the mole fraction of the solute in a similar fashion, just the moles of the solute divided by the total moles. And if these are the only two components in there, and this is a pure fraction, then this one would be equal to 1 minus the mole fraction of the solute. Right? Because they both have to add up to 1. All right, once you know that, then you can use Rails law. And there's an illustration of why Rails law works. Right, the slide B on the right-hand side has some yellow non-volatile solute in there. And that is reducing the number of molecules of solvent that can escape into the headspace. That reduces the vapor pressure. Now, this is a colligative property. So what that says is, it doesn't matter whether it's sodium chloride or any other salt dissolved in there or sugar dissolved in there. All it matters is the moles, the mole fraction of the solute, which modifies the mole fraction of the solvent. So we could put anything in there. Right? We have 1 molar sodium chloride. What molar of ions would that be? 2 molar, right? Because it makes 2 for each one. So if we put 2 molar sucrose in there, should give you the exact same vapor pressure. That's a colligative property. It doesn't matter what it is. Doesn't matter what the solute is. It only matters how much of it there is. All right. That's Rails law. That takes care of vapor pressure. Let's see. Let's just erase this part and we'll leave Rails law sitting up there. All right, boiling point elevation. What's the purpose of antifreeze in your radiator? Well, the name says antifreeze, right? So in the winter, you've got to have that antifreeze fluid in your radiator, usually at 50%. It's a 50-50 mixture of water and antifreeze. It keeps your cooling system in your car from freezing when it sits overnight and the engine's turned off. But it also raises the boiling point. Right? It depresses the freezing point so that it won't freeze and blow out your freeze plug off the engine block. In which case, you know, money. And then it also increases the boiling point so that your engine can run hotter than 212 degrees Fahrenheit or 100 degrees Celsius, which it would be with pure water. Right? And that way, you don't pop the pressure release and boil off all your water and your engine runs dry. So antifreeze does 2 things. And it's based upon its concentration. So this change in temperature here is equal to some constant that is characteristic of the solvent. Right? So in our illustration, this K would be particular for water, times this measure of concentration of the solute. And it doesn't matter what the solute is. It only matters what its concentration is. Now, we didn't talk about it earlier, so we're going to talk about it now. Little m is like molarity. By comparison, molarity is moles per unit volume, right? Molality, or little m, is equal to moles, again, per, and this is volume of solution. This is mass of solvent in kilograms. Okay? And we chose kilograms for 2 reasons. One is kilogram is the fundamental unit in the SI system. And the other is because a kilogram of water is a liter. Okay? All right. So if you express your concentration in terms of molality, then there's no volume involved. that means it doesn't matter what the temperature does, the concentration is still the same. Right? That's the important part about using molality. So that's why we use it here, because we're actually measuring a change in temperature and we don't want the concentration to change at the same time. That's two moving targets. You can't hit both at the same time. So we chose molality instead of molarity. All right. So for water, this KB is equal to 0.51. You better than that. 0.51 units of measure, degrees C per molal. Right? And that makes sense, because if you multiply molality over here, then they cancel and leave you with degrees C, which is there. And when we're talking about boiling point elevation, of course, the final temperature is going to be higher than the initial temperature, which gives you the positive value. Or you could say absolute value. Absolute value. And for this one, we use a similar format, only this one is freezing point times molality of the solute. And for water, let's go to the next one. For water, it's 1.86 degrees C per molal. Now, when we do our experiment, we're not going to use water, right? We're going to use lauric acid. It's a fatty acid. And the solute is going to be benzoic acid. Right? When you read the experiment, you'll see. So we need a different value in here for this expression. So we're talking about a change in temperature. So in order to do the experiment, you would measure the freezing point of the pure solvent, and then you would add a certain amount of solute and measure the freezing point again and subtract one from the other. And if you subtract them in the wrong order and get a negative value, it doesn't matter. Just throw the negative out. We're only interested in the absolute value. Now, let's see. There was a statement in the previous one. Let me see. Oh, standard temperature and pressure. If standard temperature and pressure are specified, STP, then standard temperature is 25 degrees C. Standard pressure is 1 atmosphere. And standard concentration, by the way, is 1 molar. In case you ever run into those situations. Okay. How does the addition of a non-volatile solute to a solvent affect the vapor pressure of the resulting solution? It decreases the vapor pressure. We looked at that already. All right, we'll talk some more about this one before we do the lab. Right. Or if we have time today, I don't know if we will, because I've only got 15 minutes left to finish this thing. The last one references osmosis. Right? And this is osmotic pressure. So we have to define, what do we mean by that? Well, we have two possibilities. A semi-permeable membrane, by definition, is one that is between two solutions, and it only allows the movement of water or gases. Nothing else. That's what semi-permeable means. Selectively permeable is a membrane that is based on pore size at the molecular level. So the pore size will be at a certain size, and molecules that are smaller than that size will go through the pores, and anything bigger will be held back. So we're going to use both types when we do the experiment. Selectively permeable membrane, I've got some special tubing that we're going to use. And for semi-permeable, we're actually going to use the cells of a piece of potato. All right. So this is how we measure osmotic pressure. If we had a solution here and a tube here with a membrane right there, and we have pure water here and pure water here, where would the level be in the tube? Right there. There's nothing driving it up. It's the water moves back and forth across the membrane equally from both sides. But if we had, say, pure water on this side, and we had a solute dissolved in this one, now let's expand the membrane. Expand the membrane. Now we've got nothing but water on this side, and we've got water plus solute on this side. Okay? Think of it in terms of probability. What's the probability of a water molecule crossing this membrane that way compared to one crossing this way? The probability is higher for water to go that direction because this solute's in the way. Right? You got solute molecules here in the way, restricting the movement of water across the membrane. So the net effect is for water to move this way. Right? And it moves a certain distance above this level until the pressure of the height of that column is effectively driving water molecules through the membrane at the same rate as they're going the other direction. So the rate this way is equal to the rate that way. Only if there's pressure on this side. That difference here is osmotic pressure. Okay? Come on. There we go. This is an illustration, right, to describe the movement. Right? The solute molecules can't move across the membrane, only water. Now, if we put a piston up here and apply a force there, we're increasing the pressure on this one to the point that now we're getting the rate of flow of water molecules going this direction faster than they're going that direction. That's called reverse osmosis. And that's one way to desalinate water. If you increase the pressure high enough on this side, you get water moving through this side, and that goes to your customers. And it increases the concentration of dissolved solids or salts in this one, and then you just slough those off. Countries that have cheap energy available, like some of the Arab countries have a lot of oil and natural gas, they can afford to take seawater and desalinate it this way. And apparently it takes less energy than distillation. Distillation is a simpler technology, and it's precedes reverse osmosis. In the lab I used to work in, we had a reverse osmosis unit in one part of the building that would take city water and pre-treat it, right, and give us a certain level of purity. And that water was piped to each one of the labs where we had a deionizing polishing unit, particularly for the research that was done in that lab. And that would finish the water off for us. But it was high maintenance. All right, let's see. Is this the last slide? Close to the last slide. No, we got a little bit to go. All right, I'll try not to spend too much time on this. This is a question that plagued me in my youth. when I first learned about the sequoia trees in California, and we were studying in school the movement of fluids inside trees, plants and trees, and we had the anatomy of the plant. I remember the xylem and the phloem. The xylem is essentially draws water in through the roots and sends it to the rest of the plant. And the phloem goes both directions. Anyway, the question in my mind was, how do you get water to the top of a 300-foot tree? And then in physics class, I learned that if you drew a vacuum, if you have water here and 1 atmosphere pressure here, and you have a tube there, and you pull the vacuum on it, right? How high would it go? Well, the maximum it could go was 33 feet. Right? That's why scuba divers say for every 33 feet you go down in the ocean, you add an atmosphere on your body. So it would only go 33 feet when you pull a vacuum. So pulling a vacuum by the tree, if you pulled a vacuum like that above it, it would only rise to 33 feet. Well, there was a theory going around that once you have that solid column of water from the roots all the way up to the leaves where you have the stomates that open, then you have the stomate is a pair of cells like this. And inside there's water. Well, when you have this water meniscus here and you evaporate the water, it's more evaporated from here, it pulls up like that, and then that also pulls on the column. So we say, well, okay, as long as you don't break the column, you can pull the water up. But some bright scientists did some experiments and found that it won't work. Right? You can't do it. So we're back to pushing the water up. So what force could push the water to 300 feet? And then the bright idea. Is there enough force, osmotic pressure generated in the roots of these trees to push water 300 feet high? So what you have to do is measure the osmotic pressure in the xylem and the roots, right? Based upon a difference in concentration of solute inside the roots versus outside. And the osmotic pressure was measured to exceed 20 atmospheres. That is huge, right? So then my question was, is 20 atmospheres enough? Is that enough to push water to the top? All right, so what I had to do was take this 300 feet and say, how tall is that in millimeters? Right, I'm going somewhere with this. So that converts it to millimeters in the height of the tree. Actually, some of them are 350 feet. And then I say, well, 20 atmospheres can be expressed as millimeters of mercury, right? 1 atmosphere is 760 millimeters of mercury. 20 of them would be 20 times that. But water is 13.6 times less dense than mercury, so we have to make that correction. Right, so that's what the second calculation is doing, is saying, okay, 20 atmospheres would be 2 times 10 to the 5th millimeter column of water. Well, it only has to go 9 times 10 to the 4th. Yeah, that's twice as much. It could go to 600 feet if we had a tree that tall. All right, so that confirms that in all likelihood, the water is getting to the top of the tree by a push of osmotic pressure from the base. All right. Now, when we express concentrations, we sort of hybridize. We hybridize molarity and osmosis, and we call it osmolarity or osmol. And it's very simple. It's simply molarity times a correction factor, I. And that correction factor is known as the Van't Hoff correction factor. And in the simplest case, if you have, say, 1 molar sodium chloride in solution, it's going to break up into sodium and chloride ions, right? So our colligative property is based upon the number of particles. In this case, number of ions. So if you have 1 molar sodium chloride, what molarity do you have of sodium and chloride ions? You have 2 molar. So the correction factor here would be 2, and the osmole would be 2 times 1 or 2 osmole. So the osmolarity of a 3 molar sodium chloride solution would be 6. Well, the I value, yes, would be 2 times 3 is 6. So you have 6 osmole. All right. Now, I'm about out of time. You ever been introduced to the concept of isotonic, hypotonic, and hypertonic? No? Okay. We do that in biology class and in A&P, anatomy and physiology. Let's start with isotonic. And we're always referring to a cell suspended in some medium, right? So the osmotic pressure is either driving water into or out of, or not at all. If the concentration of solutes inside the cell and outside the cell are equal, which naturally says that the concentration of water is the same inside and outside, the solvent is the same, then you have an isotonic solution. And there's no osmotic pressure driving water one way or the other. Okay? If you have a hypotonic solution, let's do it this way. If you have hypotonic solution, that means the concentration of water is greater than inside the cell, or the concentration of solute is less outside. So the movement of water is going to be toward the hypotonic solution. And that's this one right here. A hypertonic solution has a greater concentration of solute outside the cell, or a lesser concentration of water, which means water is going to move into the cell. Excuse me.
Oh.
Yeah, I got it backwards, don't I? Hold on a second. Hypotonic outside means water moves in. Yeah, you're right. I got it backwards. Hypotonic means water moves in. Hypertonic means water moves out. So what does that look like? Okay. Let's use blood cells as an example. The one on the right is a normal shape for a blood cell. Right? It's biconvex, biconcave. And it would neither swell nor shrink. Right? Isotonic would be perfect. If you put the cell in pure water, so for instance, a hypotonic solution, then water is going to move into the cell and eventually explode. And if it's hypertonic solution, then water is going to move out of the cell and we get crenation. Now, what's an isotonic solution for the human body? Well, it's 0.9% by mass, mass volume of sodium chloride will give you that. But EMTs, when they travel around, they keep isotonic solutions so that they can rehydrate a patient on the way to the hospital or get an IV started. And as long as the patient's not diabetic, they'll use D5W, they call it. Dextrose 5% by weight. Actually, it's mass volume. But that 5% is very close to isotonic. Right? If they have a diabetic patient, then they have to go to a different solution that doesn't have an impact on their blood sugar. Right? Because if they did that to a diabetic, then by the time they got to the hospital, they'd be in shock. Okay. Let's see. All right. This slide says that at the bottom is if you use 0.9% sodium chloride as an isotonic solution, physiologically, that's true. It will be isotonic with your tissues, but it's going to overload your kidneys with 10% too much sodium and 50% too much chloride. So you don't want to be on that solution for very long. Otherwise, it'll damage your kidneys. And the article that I drew this from is listed there at the bottom if you want to take a look at it. All right, what's an isotonic solution? Osmotic pressure is equal on both sides of the cell, both sides of that membrane. The osmolarity is simply the molarity times the Van Hoff correction factor, the I, and that's based upon the dissociation of the molecule, right? What would be the Van Hoff correction for glucose? 1. 1 molar glucose is 1 osmole because it does not dissociate. All right, we're out of time. I'm going to have to skip these. Sorry. I'll record it slowly. So if you want to go back and look at it, you can get the right answer for that one. And then for this one, well, that just gives you the answer. Okay.